Imagine, just for a moment, that you are behind the wheel of a car.
Okay. What kind of car are we talking about here? A beat-up sedan? A sports car?
It doesn't really matter. Let's say it's a fast one, something with, a lot of power under the hood. But here's the context that matters. It is night, pitch black,
Mm-hmm.
and you are driving down a steep, winding mountain road. The kind of road where the turns are sharp, the drop-off is steep, and your palms start sweating just looking at the GPS.
I know the kind. White-knuckle driving. You're gripping the steering wheel so hard your fingers turn white.
Exactly. Now let's raise the stakes. Imagine there are no guardrails. No metal barriers, no concrete walls protecting you from the edge, just the asphalt, a bit of loose gravel, and then nothing, just the abyss.
That sounds absolutely terrifying.
It gets worse. Suddenly, your headlights flicker out.
No.
You are careening around hairpin turns in total darkness. The car is skidding on the gravel. You can hear the tires screeching near the edge. And in the back seat,
What's in the back seat?
your children are screaming.
Okay, this is officially moved from a stressful scenario to a recurring nightmare. I think I've actually had this dream.
It does feel like a nightmare, doesn't it? But according to the source material we are unpacking today, this isn't a bad dream.
No.
This is the current literal reality of humanity. We are in the driver's seat of the Earth system. We are speeding up, and we are driving blind.
It is such a visceral image.
Yeah.
And it comes straight from the introduction of the book we are diving into today, Breaking Boundaries, The Science of Our Planet. It's written by Owen Gaffney and Johan Rockström, and it includes a very pointed, very intense foreword by Greta Thunberg.
And look, I know what you, and probably you, listening right now are thinking, great, another doom and gloom deep dive about how the world is ending.
Yeah, I'll just go ahead and skip this one, thanks.
Right, and I'll be honest, when I read that opening analogy, the car, the cliff, the screaming kids, I felt that pit in my stomach. You know the one, the climate anxiety pit.
It is a natural reaction. I mean, we are bombarded with bad news constantly.
Yeah.
It's easy to feel like the only option is to just shut down.
But the mission of this deep dive, and really the mission of the book itself, isn't just to scare us. It's actually the opposite. It's about control. It's about figuring out how to turn the lights back on.
Precisely. The anxiety comes from the feeling of helplessness, right?
Exactly.
The feeling that we are careening off a cliff and can't do anything about it. But Rockström and Gaffney argue that for the first time in human history, science can actually tell us where the guardrails are.
We can see the edge of the road.
We can. We aren't actually flying blind anymore, or at least we don't have to be. We have the data to identify what they call the safe operating space for humanity.
So instead of just screaming as we go off the cliff, we can actually turn on the high beams, see exactly where the edge is, and, steer away from it.
That is the goal. We are looking at a diagnosis of a patient Earth rather than writing an obituary. Rockström and Gaffney are trying to unpack what they call the most important scientific insights of the 21st century. And it's crucial to state up front, this is not just about climate change.
Right, that's a big distinction I want to make early on. Usually when we talk about the environment, it's all carbon and temperatures.
Climate is a huge part of it, obviously.
Yeah.
It's like the headline act. But the framework here covers the entire life support system of the planet. It's a holistic view.
Okay.
It's about the water, the soil, the air, the ice, and all the living things that hold it all together.
So let's get into the diagnosis then. If we are going to understand the patient, we need to understand the patient's history. And the authors take us back, way back.
Deep time.
We are talking 4.5 billion years deep. Why is this context necessary? Why can't we just look at the last 100 years to understand what's happening?
Because if you want to understand the trauma the Earth is facing now, you have to look at what it used to be. You have to understand the baseline. The authors distinguish between different versions of, almost like software updates on your phone.
Okay, walk me through the versions. What was Earth 1.0?
Earth 1.0 was the early Earth, Hadean Earth, basically a dead rock being just bombarded by meteorites, molten lava, toxic atmosphere.
Not a great vacation spot. 0 stars on Yelp.
Definitely not.
Yeah.
Then, over billions of years, you get upgrades. Earth 2.0 involves the first microbial life. But Earth 3.0 is where it gets really interesting. That's when photosynthesis arrives.
Okay.
This is a massive upgrade. Oxygen builds up, the atmosphere changes, and life starts to actually terraform the planet. But the version we are most interested in, the one we live on, is Earth 4.0, complex life.
This brings up that pale blue dot perspective, doesn't it? The whole Carl Sagan idea.
Exactly. Imagine you are an alien astronomer on a distant exoplanet looking at Earth 4.0 through a high-powered telescope today. What do you see?
I assume I'd see a beautiful blue marble. Clouds, oceans, green continents.
You would. But if you had sensitive instruments, spectrometers and the like, you would see a planet in trauma. You would see rapid atmospheric changes happening in the blink of a cosmic eye.
In real time.
You'd see ice sheets collapsing in real time. You'd detect shifting ocean acidity. The biomarkers of the planet are just going haywire.
It's interesting you say trauma because that implies an external force causing damage. Usually in the past, that force was a volcano or an asteroid. But today, the force is us.
And that is the hardest thing to really wrap your head around, the scale of us. We still think of ourselves as these small creatures running around in a vast wilderness, but there is one statistic from the book that I think perfectly encapsulates just how much we have changed the physical composition of life on this planet.
Ooh.
It's a fact that I've started using at dinner parties, usually right before I ruin everyone's appetite.
Oh, I love those facts. Lay it on me. I'm ready to have my mind blown.
Okay, picture a giant weighing scale. A scale big enough to weigh all the mammals on Earth, every single one.
Okay, got it. Giant scale.
On one side of the scale, we put all the wild mammals.
Yeah.
And I mean everything. Elephants, giraffes, tigers, badgers, whales, mice, porcupines. Everything that we think of as nature or wildlife.
The David Attenborough stuff, the Serengeti, the Amazon.
Right. On the other side of the scale, we put humans. And we put our livestock, the cows, pigs, sheep, and chickens that we raise to eat.
Okay, so wild animals on the left, humans and cows on the right. What's the split?
Take a guess. What does your gut tell you?
I mean, I know there are billions of humans, but nature is big. The oceans are full of whales. The savannas are full of wildebeest, I'd guess. Maybe 50-50. Or maybe 60% humans and livestock, 40% wild animals.
Humans and our livestock now make up 96% of the biomass of all mammals.
Wait, repeat that, 96.
86%.
So that leaves 4%.
4% for everything else. All the elephants, all the rhinos, all the dolphins, all the deer. Everything we call the wild is just a tiny, shrinking 4% fragment on the edge of the scale.
That is staggering. It's honestly hard to process. It completely dismantles the idea that humans are just living in nature. It sounds more like humans are consuming nature.
We are.
We have physically replaced the wild world with a human-designed world.
We have. We have terraformed the planet to serve us. And this is why the authors argue we need a new framework. We aren't small anymore. We are giants. We are the dominant force. And to understand how fragile this system is that supports this massive human biomass, we have to look at the climate history.
Yeah.
Specifically, the discovery of the Ice Age cycles.
This part of the book was fascinating because it reads like a detective story, and the hero isn't who you'd expect. It's not some fancy professor from Oxford or Harvard.
No, it's the Scottish janitor.
James Crowell. I absolutely love this story. So set the scene for us. It's the 19th century.
Right, mid-1800s. You have the scientific elite of Victorian Britain guys in tweed suits at the Royal Society trying to figure out why the Earth has these massive freezes, these ice ages. They see the geological evidence, giant scratches on rocks where glaciers used to be, but they have no idea why it happens.
They're just scratching their heads.
Completely. And the guy who crafts the code is mopping floors at Andersonian University in Glasgow.
He was. James Crowell was a self-taught intellect. He came from a poor background, had various jobs that didn't work out, and eventually took a job as a janitor at the university. But he had an insatiable curiosity.
Yeah.
He actually convinced his brother to do most of his janitorial work so he could spend his shifts in the university library.
That dedication.
It's
Here, take the mop. I need to calculate orbital mechanics.
It sounds like a movie script, but it's true. He sat there reading books on physics, astronomy, and geology.
Yeah.
And in 1864, he published a paper that changed everything. He figured out that the cause of the ice ages wasn't some internal mechanism of the Earth-like volcanoes going dormant, but the Earth's orbit itself.
The wobble.
The wobble.
See, we think of the Earth orbiting the sun in a perfect circle, like a plate on a table. But it doesn't. Over tens of thousands of years, the orbit shifts from circular to elliptical, more like an egg shape.
Okay.
And the Earth wobbles on its axis, like a spinning top that's slowing down.
And Kroll, and later the Serbian mathematician Milutin Milankovic, who perfected the math, figured out that these wobbles change how much sunlight hits the planet.
Specifically, how much sunlight hits the North in summer. That is the critical variable.
But here's the thing that blows my mind, and the authors make a big point of this. They call it the hair trigger. Because these orbital wobbles, they are tiny, right?
So tiny.
We're talking about minute changes in distance from the sun.
That is the key insight. The change in incoming solar energy is negligible. It's a fraction of a watt per square meter. It shouldn't be enough to freeze the planet. If Earth were a dead rock like the moon, that change in sunlight would barely register. The temperature would drop a fraction of a degree.
So why does it cause an ice age where New York is buried under a mile of ice?
Because Earth is not a stable rock. It is a dynamic reactive system. It amplifies the signal.
A feedback loop.
Exactly. Imagine the orbit causes just a little bit of snow to survive the summer in Canada or Scandinavia. Just a patch.
Okay. A little leftover snow.
That white snow is highly reflective. It acts like a mirror. It reflects sunlight back into space. This is the albedo effect. Because it reflects the heat, the air above it gets colder.
Which means the snow doesn't melt. In fact, more snow falls.
Exactly. And that new snow reflects even more heat. It's a feedback loop. The planet cools itself down. And then there's a second feedback loop.
Oh, there's more.
As the oceans get colder, they suck up more carbon dioxide from the atmosphere because cold water holds more gas than warm water. Just like warm soda goes flat faster than cold soda.
So the CO2 levels drop, which weakens the greenhouse effect, which cools the planet even further.
Right, so a tiny, tiny orbital nudge sets off a massive cascade that ends up burying the northern hemisphere in ice. That is the hair trigger.
It makes the Earth sound incredibly sensitive, almost temperamental. It's not this immovable object. It's a system waiting for a push.
It is. For the last, say, 2.7 million years, Earth has been oscillating back and forth on this hair trigger. Deep freezes, ice ages, and short warm periods called interglacials. It's rhythmic.
Like a heartbeat.
The authors describe it as a heartbeat. And this isn't just theory. They have the receipts, the ice cores.
It is the forensic evidence. By drilling miles down into the Antarctic ice, scientists can extract cylinders of ice that contain tiny bubbles of ancient air. They can literally sample the atmosphere from 800,000 years ago.
And when they analyze that air, what do they see?
What do they see?
They see a perfect synchronization. It looks exactly like an EKG in a hospital, beat after beat. CO2 goes down, temperature goes down, ice age. CO2 goes up, temperature goes up, warm period. Up and down, regular as a clockwork.
But here is where the story shifts from fascinating history to urgent warning. The authors talk about the broken heartbeat.
Right. In that entire 800,000-year record, through all the wobbles, all the volcanoes, all the solar shifts, nature's heartbeat kept carbon dioxide within a very strict, very tight range.
What was the range?
It went down to about 170 parts per million ppm during the coldest ice ages, and it went up to about 280 ppm during the warmest periods, never higher. 280 was the absolute glass ceiling. Nature simply did not allow carbon to go higher than that.
Okay, so 280 is the historical maximum, the do not exceed line. Where are we today?
We are over 415 parts per million and climbing every year.
So if you look at that graph, you have this steady rhythmic wave for almost 1 million years. And then suddenly, in the last blink of an eye, the last 100 years, you have a vertical line shooting straight up off the chart.
It looks like a cardiac arrest.
Yeah.
We have completely broken the natural cycle. We are putting pressure on the system that hasn't been seen in millions of years. And remember the hair trigger. We are pushing that trigger harder than nature ever has.
And the last time CO2 was this high, humans didn't exist. The continents were in different places. There were trees growing at the South Pole.
Exactly. We are venturing into deep unknowns. We are literally uncharted territory. Before we get to the consequences of breaking the cycle, we need to talk about the good times. The authors focus heavily on this specific warm period we've been living in for the last 10,000 years.
The Holocene.
The Holocene.
They call it the Goldilocks epoch. I love that name because it implies everything was just right. But I think people hear Ice Age ending and they just think, oh, the weather got nice.
But it's more than that, isn't it? It wasn't just warmer, it was calmer.
Much more. The Holocene is the name geologists give to the last 10,000 years. We came out of the last ice age, and instead of the temperature bouncing around wildly, it settled. It flattened out. For 10,000 years, the average temperature of Earth didn't fluctuate by more than plus or minus 1 degree Celsius.
Plus or minus 1 degree, that is an incredibly flat line.
It's freakishly stable, and the authors make a huge point about this. This stability isn't just a nice coincidence. It is the foundation, the literal bedrock of everything we call civilization. Can you connect the dots there? How does a stable temperature lead to iPhones and skyscrapers?
Well, look at the timeline. Before the Holocene, humans were around. We've been Homo sapiens for at least 200,000 years. We were anatomically modern. We had the same brains, the same capacity for language, the same social skills. But for 190,000 years, we were nomads.
Right. Hunter-gatherers?
We didn't build cities. We didn't plant farms.
Oh, God.
Because we couldn't. The climate was chaotic. You couldn't plant a crop because you didn't know if next year would be a drought, a flood, or a freeze.
Yeah.
You had to stay mobile to survive. You had to follow the food.
But then the Holocene hits. The weather calms down. The seasons become predictable. You know that if you plant in spring, the rain will come.
And suddenly, almost instantly, in geological time, independently, all over the world, agriculture emerges.
All at once?
In the Middle East, in China, and the Americas. We figure out we can plant seeds and know they will grow, so we stop moving. We build villages to store the grain, then towns, then cities, then pyramids, then democracies, then the Industrial Revolution, then the Internet.
It's humbling to think about it that way. We tell ourselves history is about great leaders and wars and inventions. But really, all of our achievements were basically allowed by the weather being nice for a while.
It wasn't just nice, it was reliable. Reliability is what allows for investment, for planning the future.
Yeah.
We took it for granted. We assumed that stability was a permanent feature of the planet.
The sun rises, the rain falls, the crops grow.
We thought that was just how Earth worked.
Yeah.
But the source material highlights a dramatic moment where that assumption was shattered, the stop moment. This is a great anecdote in the book.
Okay, tell me about it.
It involves Paul Crutzen. He was a Dutch atmospheric chemist, won the Nobel Prize for his work on the ozone layer. A giant in the field.
So it's the year 2000. Where is he?
He's at a scientific conference in Mexico. The room is full of experts discussing environmental changes. And people kept referring to the Holocene. In the Holocene, we see this. The Holocene record shows that.
And Crutzen gets annoyed.
He gets agitated. Crutzen was usually a very calm, polite guy. But he starts shifting in his seat. He's getting red in the face. Finally, he just loses it.
What did he do?
He interrupts the speaker. He stops proceedings and says, "Stop. We are not in the Holocene anymore."
Talk about a mic drop moment. The room must have gone silent.
Dead silent. It was a scandal. They asked him, "Well, where are we then?" And he was grasping for a word. He hadn't prepared a speech. He just blurted out, "We are in the Anthropocene."
The Anthropocene, from anthropos, meaning human, the age of humans.
It was the realization that we are no longer just passengers. We are now the primary driver of change on the planetary surface. We move more sediment than all the rivers combined. We alter the atmosphere faster than volcanoes. We have ended the Goldilocks epoch.
So if the Holocene is over, when did the Anthropocene really begin? The book points to a specific era, and it's surprisingly recent. They call it the Great Acceleration.
This is fascinating because you might naturally think the damage started with the Industrial Revolution. Coal, steam engines, Dickensian London in the 1800s.
Right.
And sure, that started the trend. CO2 started ticking up.
But the curve wasn't steep yet. It was a gradual slope.
Correct. If you look at the data, and the authors present these hockey stick graphs, everything really explodes in the 1950s.
The 1950s, post-World War II.
Exactly. You have this convergence of three massive forces. First, cheap energy oil became the blood of the economy. Second, technological leaps technology developed for the war was repurposed for peace. Chemical fertilizers, mass production. And third, globalization.
And suddenly, the curves go vertical.
Vertical. Population, water use, fertilizer use, paper consumption, tourism, telephones, McDonald's restaurants, everything spiked simultaneously in 1950.
This brings us to the lily pond. This is a riddle the authors use to explain exponential growth, and honestly, it's the best explanation I've ever heard. I feel like humans are really bad at understanding exponential numbers.
We really are.
We understand linear things, 1, 2, 3, 4, but we don't get doubling.
We don't. Our brains aren't wired for it. We are linear thinkers in an exponential world. So the riddle is helpful. It's a classic French riddle. It goes like this. You have a lily pond. You plant one lily. Each day, the lilies double in size.
Okay.
If it takes 30 days for the lilies to completely cover the pond and suffocate it, on what day is the pond half full?
Okay, so let's do the math. If it doubles every day, and it's full on day 30, then it must be half full on the previous day, day 29.
Exactly. Mathematically, that's simple. But think about the psychology of that. Imagine you are standing by the pond on day 25. The pond is massive.
Yeah.
The lilies are just a tiny patch in the corner. You look at it and say, I have plenty of time. This isn't a problem.
On day 27, it's still mostly empty water. Even on day 29, you look at it and say, oh, it's only half full. We have 50% of the pond left. That's tons of space. We can keep growing.
And then one day, later day 30, game over, the pond is dead.
That is the danger of exponential growth. It moves slowly and then suddenly, all at once.
The discussion in the source material really hammers this home. Humanity is likely sitting on day 29. We look around and think, hey, the economy is growing, supermarkets are full, we have more gadgets than ever, everything seems fine. But we don't realize that one more doubling takes us to the wall.
That is terrifying. It explains why it's so hard to get people to act on climate change. Because until you hit the wall, it feels like you have space. It feels like you can just keep growing.
Precisely. We mistake the speed of the car for the stability of the road. And that brings us back to the core mission of this deep dive. If we are on day 29, how do we stop from hitting day 30?
We need the guardrails.
We need to know where the limits are. We need those guardrails we talked about in the intro.
The planetary boundaries.
This is the framework developed by Johan Rockström and his colleagues. The idea is simple but profound. If the Holocene is the only state we know can support civilization, how do we ensure we stay as close to Holocene conditions as possible? What are the hard lines we cannot cross?
They identified 9 of them. 9 boundaries. And in the book, they break them down into categories. Let's start with the big 3. These are the regulators of the whole system.
Right. First and foremost, climate. We've talked about CO2. The safe limit, established by looking at the Holocene data, is 350 parts per million.
And we are at 415 plus, say.
We are way past that. We have crossed the boundary. We are in the danger zone. This is why we are seeing extreme weather, heat waves, and storms. We have left the safe space.
Okay. Second.
The ozone layer. Now, this is actually a success story, and it's important to dwell on it for a second. In the 1980s, we were spraying CFCs everywhere.
Yeah.
Hairspray, refrigerators, air conditioners.
Right.
We didn't know they were destroying the ozone layer, which protects us from UV radiation.
We were literally burning a hole in the roof of the world.
We were, and we nearly broke the boundary. If we hadn't acted, life on land would have become impossible due to radiation. But here's the kicker. We got lucky. This is a detail Rockström loves to point out. The industrial chemicals we used happened to be based on chlorine.
Okay, chlorine.
Chlorine destroys ozone, but not that fast. There's another element called bromine. It sits right next to chlorine on the periodic table. It has almost identical properties. It could have worked just as well for keeping our fridges cold. But bromine destroys ozone about 100 times faster than chlorine.
Whoa.
If the chemical industry, just by chance, had decided to use bromine instead of chlorine in the 1960s, the ozone hole would have opened up everywhere, all at once, by the mid-1970s. We wouldn't have had time to discover it. We wouldn't have had time to sign a treaty. We would have been cooked, literally.
That is a chilling thought. We survived by chemical luck.
We did, but we also survived by action. We signed the Montreal Protocol. We banned the chemicals. And now the ozone is healing. We are back within the safe boundary. It proves that we can pull back from the edge.
So we have 1 failure, climate, and 1 success, ozone. What's the third big one?
The ocean, specifically ocean acidification. This is often called the evil twin of climate change.
How does it work?
The ocean absorbs a huge amount of our carbon dioxide, about a quarter of it. That's actually good for the climate in the short term because it keeps that CO2 out of the air. It acts like a sponge. But there is a cost. When CO2 dissolves in water, it turns into carbonic acid.
It changes the chemistry of the water.
It drops the pH. And for marine life that builds shells, clams, oysters, corals, plankton, this is devastating. Acid dissolves calcium carbonate.
It's like osteoporosis for the ocean.
Exactly. If the water gets too acidic, the base of the food web literally dissolves. Their shells get thin and brittle, and if the plankton die, the fish die, the whales die, and the people who depend on the ocean die. We are approaching that boundary very fast.
Okay, so that's the big 3.
Yeah.
Then they talk about the biosphere, the living part of the planet.
This is about resilience. The big 3 set the physical conditions, but the biosphere determines how well the Earth can handle shocks. There are 4 boundaries here. First and most obvious, biodiversity.
And this is a red alert in the book.
A screaming red alert. We are shredding the web of life. Extinction rates are 100 to 1,000 times higher than the background rate. And it's not just about saving cute pandas or tigers. It's about the genetic library of the planet. Every time we lose a species, we lose a solution that nature spent millions of years refining. We are burning the library before we've even read the books.
And land use.
This is mainly about forests. Forests are the lungs of the planet and the home of biodiversity. To stay safe, the science says we need to keep about 75% of the Earth's original forests intact, especially the tropical rainforest and the boreal forests up north.
Where are we now?
We are down to 62%. We've crossed that boundary. We are turning forests into farms, soybean plantations, and parking lots.
And then there's fresh water and nutrients.
Freshwater is interesting because we are hitting limits on both blue water, rivers, and lakes, which we are draining dry in green water, the moisture in the soil, which is changing because of climate change. But nutrients. This is the silent killer, nitrogen and phosphorus.
This is fertilizer, right?
Yes. In the early 20th century, we invented the Haber-Bosch process. It allows us to pull nitrogen out of the air and turn it into artificial fertilizer.
Yeah.
It was a miracle. It prevented famine. It is the reason there are 8 billion people on Earth.
So what's the problem?
The problem is efficiency. We use so much of it that the plants can't absorb it all. It runs off into rivers, then into the ocean. It feeds massive blooms of algae. When the algae die, they rot, and the rotting process sucks all the oxygen out of the water.
Creating dead zones.
Massive dead zones where nothing can live. We have massively crossed this boundary. We are poisoning the planetary system in an attempt to feed the human system.
It's such a paradox. We solved one problem, hunger, and created a planetary crisis.
That is the recurring theme of the Anthropocene. Unintended consequences. We pull a lever to fix X, and we break Y.
And speaking of unintended consequences, we have the final category of boundaries, the aliens.
Novel entities. This is arguably the scariest category because it's the unknown unknowns. This is all the man-made stuff we introduce that nature has never seen before. Plastics, nuclear waste, heavy metals, and 100,000 different synthetic chemicals.
Well, the book uses a really disturbing metaphor here, the paperclip maximizer.
It's a thought experiment from AI research, but it applies perfectly here. Imagine you program an artificial intelligence with one single, simple goal. Make paperclips. That's it. Just make as many paperclips as possible.
Full is harmless.
At first, but the AI gets smarter. It realizes it needs resources. It starts converting your house into paperclips, then your town. Then it realizes humans are made of atoms that can be turned into paperclips. Eventually, it consumes the entire Earth just to fulfill its programming.
So in this metaphor, we are the AI.
Or our economy is. We have programmed our global economy to maximize stuff, production, consumption, GDP. We are churning out chemicals and plastics to fulfill this goal without an off switch that considers the stability of the planet. We are turning the Earth into paperclips.
That is a lot to process. It really frames consumerism in a horrifying light. But there is one more category in the alien section, aerosols.
Air pollution, smog. It's not just about health, though it kills millions of people a year. These brown clouds of smog, especially over industrial areas in Asia, actually block the sun. They reflect sunlight.
So they cool the planet.
They do. They mask the warming, and this is the Faustian bargain. If we cleaned up the air tomorrow, which we should for our health, the planet might actually heat up faster because we lose that artificial dimming effect.
Wow.
We are shielding ourselves from the full impact of our CO2 with our own pollution.
So let's look at the scorecard. We have walked through the 9 boundaries, and it's not great. We have crossed 4 of them significantly. Climate, biodiversity, land use, and nutrients. We are in the danger zone.
We are, and this leads us to the most critical concept in the book. The reason why crossing these boundaries is so dangerous, it's not just that things get gradually worse, it's that we might trigger tipping points.
The authors use the Rocky Balboa analogy here.
Right. Earth is resilient, like a boxer. He can take a punch. We pump out CO2, the oceans absorb it, we cut down trees. The remaining forests grow faster to compensate. Earth absorbs the blows. It wants to stay in the stable state.
But even Rocky eventually gets knocked out.
Exactly. Resilience is not infinite. You hit a point where the system changes state. It snaps. And the transition is sudden. It's not a gentle slope, it's a cliff. Once you fall off, you can't climb back up. This is called hysteresis.
And the scary part isn't just one tipping point, it's the domino effect. These things are connected.
This is the hothouse Earth scenario the authors warn about. It's a nightmare scenario of cascading failures. Let's play it out. Imagine the Arctic ice melts because of global warming.
Okay. Less white ice, less reflection, more heat. We know that loop.
Right. That extra heat accelerates the melting of the Greenland ice sheet. Now you have all this cold, fresh water dumping into the North Atlantic Ocean.
And that disrupts the currents.
Yes. It slows down the AMOC, the Atlantic Meridional Overturning Circulation. This is the massive conveyor belt that moves heat around the world. If that slows down, heat gets trapped in the southern hemisphere.
Okay, so the south gets hotter.
That changes rainfall patterns over the Amazon. The Amazon dries out. It shifts from a wet rainforest to a dry savanna.
And a dry savanna burns.
Exactly. So the Amazon, instead of being a carbon sink that absorbs our pollution, starts burning and releasing massive amounts of carbon into the atmosphere.
Which heats the Earth even more.
Which melts the permafrost in Siberia, releasing methane. You see the pattern. It's a cascade. Once the first domino falls, it becomes very difficult, maybe impossible, for humans to stop the rest.
That is the hothouse Earth, a planet that has taken over the controls. Even if we stopped all emissions today, if we've already tipped the first domino, the planet drives itself to 4 or 5 degrees of warming.
And as the quote of the book says, the difference between 2 degrees and 4 degrees is human civilization. At 4 degrees, the equator is uninhabitable. Agriculture collapses. Sea levels rise by meters. It is a different planet.
Okay, let's take a breath, because that is heavy. We are talking about the potential collapse of the systems that support us, but the book isn't just about physics and chemistry. It talks about us, the human element.
Mhm.
Why are we doing this? We call ourselves Homo sapiens, wise man. Are we actually wise?
It's the paradox of intelligence. The authors dive into our evolutionary history. We evolved to survive in small groups on the African savanna. Our brains are hardwired for if and then logic. We are amazing at solving immediate local problems. If I plant this seed, then I get food. If I build this engine, I get power.
We are tool makers. We see a problem, we invent a tool.
We are fantastic systemizers. We are amazing at the gas pedal, but we are terrible at the brakes. We struggle to see long-term complex consequences. Our brains didn't evolve to care about what happens to the atmosphere in 50 years. We care about what happens to our tribe tomorrow.
So we invented fertilizer to solve hunger, gas pedal, but didn't foresee the dead zones, no brakes. We drilled for oil to power the world, but didn't foresee the climate crisis.
Exactly. We are godlike in our technology, but still primate-like in our foresight. And there's another layer to this human element that Greta Thunberg highlights in her foreword: inequality.
This was a stark set of numbers. It really challenges the idea that humanity caused this.
It is essential to understand this isn't just all humans acting equally. The data shows that the top 1% of income earners globally emit 81 tons of CO2 per person per year.
81 tons.
The bottom 50%, the poorest half of the world,
How much?
0.76 tons.
Wow. So the top 1% are emitting more than 100 times what the bottom half of the world is.
It challenges the narrative that we are all in this together. Thunberg argues that we are fighting to maintain a lavish, high-consumption way of life for a very small few at the expense of the stability of the planet for everyone else. It's a justice issue as much as a scientific one.
So where does this leave us? We have broken the boundaries. We are teetering on tipping points. We have this evolutionary blind spot and massive inequality. Is it game over? Should we just enjoy the drive off the cliff?
No, absolutely not. And this is where the authors pivot to the Earthshot.
The Earthshot, like the moonshot, but bigger.
Much bigger. The moonshot in the 1960s was about going somewhere. It was a technological sprint. The Earthshot is about staying here. It's about securing our future on Earth. The authors argue that the 2020s, this decade right now, is the decisive decade. We have to transition our entire economy faster than the Industrial Revolution happened.
That sounds impossible, given how slow politics moves.
It sounds impossible, but remember the lily pond. Remember exponential growth.
It works both ways.
Exactly. We are seeing exponential growth in solutions. Look at renewable energy. 10 years ago, solar was expensive. Now, in most parts of the world, solar is the cheapest electricity in history. Cheaper than coal, cheaper than gas.
And electric vehicles, they are following the same S-curve?
We are seeing exponential growth in awareness, in social movements, in corporate commitments. We are starting to see the positive tipping points.
So we can flip the curve.
We can. The authors believe we can get back within the safe operating space. We can rewild the planet, giving space back to nature to restore that biodiversity boundary. We can fix the food system shifting to regenerative agriculture to fix the nutrient boundary. We can decarbonize energy to fix the climate boundary. We know how to do it. The guardrails are there. We just have to steer the car away from the cliff.
You mentioned earlier that you carry something in your pocket to remind you of this.
Yes, it's something Johann Rockström mentions in his talks. A small blue marble.
A marble.
It's a reminder of perspective. For most of human history, we were a small world on a big planet. We were tiny. The planet was infinite. We could dump trash, burn forests, and the planet was too big to notice.
But now...
Now that marble represents the shift. We are a big world on a small planet. We are the giants. We have filled the jar.
And with that size comes responsibility. We aren't children anymore. We are the stewards.
It does. The authors pose a final provocative question that I think is the perfect place to land this deep dive. They ask us to think about asteroids.
Asteroids.
We know asteroids have wiped out life on Earth before. The dinosaurs were taken out by a rock from space. It was an impact event.
Right.
Right now, humanity is acting like an asteroid. Our impact on the planet is as destructive and rapid as a meteor strike. We are the impact event. But there's one crucial difference.
An asteroid doesn't have choice.
Exactly. An asteroid is just physics. It follows a path. But we have agency. We have consciousness.
So the question is, if we are the asteroid, can we also choose to be the shield?
That is the question. We spent 10,000 years fighting nature to survive. We thought nature was the enemy, the wilderness to be conquered. Now we have realized that nature's survival depends entirely on us, and our survival depends entirely on nature.
It's a complete reversal of the relationship.
It is. The future isn't written. We aren't just passengers in the runaway car anymore. We are the drivers. We can hit the brakes. We can turn the wheel. But we have to do it now.
As the book concludes, the future is not written. It is built, choice by choice, boundary by boundary.
Couldn't have said it better myself.
That's it for this deep dive into breaking boundaries, a scary but ultimately hopeful look at the science of our planet. Thanks for listening.
Stay curious and mind guardrails.